And don't say anything too loud because they'll hear you. Good morning, everybody. I am so tired. I'm running on fumes. I was dropping my daughter off at the airport at 4 a.m. yesterday. She's leaving on an 18-month mission for our church, so I won't see her for 18 months. So I was emotionally a wreck. And then at 5 o'clock in the morning, I was giving live interviews with the local TV stations here about the building. And then I had labs all the way until 2 p.m. So that's a pretty intense day for me. But so we'll see how well this goes. I might end up sitting down, and I do apologize if I do that, but it's either that or fall down. Let's see here. How's we getting on Wiley Plus and stuff? Okay, we having trouble? What's pain point? No. Those of you that bought a 6-month subscription could get a surprise, like in February or so, when it suddenly locks you out. Just be aware of that, right? I'm sure there's a way to look up how much time you got left, but I don't know what it is. If you bought the year access, you're going to be fine. But just make sure that's all working. Some people have been emailing me with like technical problems. The sheet, it's not popping up correctly, but we'll sort those out. Remember, tomorrow, Grasp, good day to make sure all of that's working. As the terrible teacher that I am, I don't believe there's any homework due this Saturday or Monday or anything. I messed up. I should have just really hit you with it, but no, we need to get through some stuff. But I think we're all set to go. So Monday, what's happening? No school, right? I'm sleeping in that day. I usually don't sleep in. I'm sleeping in that day. It's Martin Luther King Day. Go out and celebrate, take a day off, do extra work, whatever it is that you've got planned, right? And then that means that the lab that was supposed to be due, that math lab, which is due on Monday, is going to be due the lab after that. Whatever. We get screwed up routinely by holidays in this semester because of our Monday lab. I don't know yet what I'm going to do about your first exam autopsy, because you take your first exam, and then I think we have President's Day weekend. And so like Friday and Monday we're off, and the Monday would have been when we would do the exam autopsy. So I'm trying to decide, maybe we can do the exam autopsy in here and maybe lecture in lab, or I can be cruel and make you wait 2 weeks. I don't know what I'm going to do, okay? But I'll figure it out. We'll get there. I think the schedule is wrong as far as that's concerned. All right, we were doing Coulomb's law, right? We were talking about this R vector thing. Just to reiterate a couple of things. R vector, not a radius, a distance. Where does it start? On whatever is causing something to happen. Charge, gravity, mass, electric field, whatever. The thing that's causing something to happen is where R vector starts. And then where does it end? At the point where you're trying to figure something out. Like if we're asking for the force on little q1, then R doesn't start on q1, it ends on q1, right? It starts on q2. So just keep that in mind. I did go and double check and make sure I read the book correctly. When your book says like F32, okay, what it means is it's the force on 3 because of 2. Is that what I said on Tuesday? I hope that's what I said on Tuesday. Okay. So what I want to do, play a little stupid video, and then I want to do an example of calculating Coulomb's law, sort of with Mr. Balogh's way, the physics way, not exactly the way your book does it, but again, the more you see different ways, the better off you're going to be in the long run. Let me switch gears and hit that. Nope, you were supposed to play a video.
Electricity attracts when it acts between charges of different signs.
Whoa! That negative
But acting
R hat,
between charges that are the same,
and then
it
there's the
repels.
positive R hat. Positive meaning away, right?
According to Coulomb's law,
The force two charges exert on a third is the vector sum of the forces each alone would exert. In fact, the forces from any number of positive charges and negative charges add together as vectors.
See how it's 3D?
So the total force is still calculated from Coulomb's law.
Ah!
Notice
Wait, don't
that
panic,
positive
don't panic.
charges are shown in red and negative charges are shown in blue.
Do you like the trippy music? All right, so, oh my gosh. What's this part right here? That's Coulomb's law, isn't it? Yeah. I keep forgetting I have two of these now. This is Coulomb's law, right? Right there. What's the sum on the front mean? Add up, right? Like if we want to find the force on that red one down there, how many other vectors are we going to have to deal with? 3 more, right? There's 3 other charges. And so does the red one on the bottom experience a red one from the top? A force? Yes. And what about blue one over there? Yes. And what about, right? And so all 3 things are applying force. We can find each of those forces individually. And because they're vectors, we can then add them all up as vectors. That is our plan of attack. Like we had forces, net force in physics 4a, acting on an object, and components, and all of those things, right? Post-traumatic stress kicking in from chapters 5 and 6 yet? We're going to do the same thing, but we're going to use Coulomb's law. All right, so that's the goal. Let's get there. Nope, come on. There we go. All right, so real quick. So I know you reviewed some vectors in the math preview, but let's just talk about vectors really, really quick, and then I'll get to the example. Vectors can be represented by their components, and what are these magical hat symbols we use for the directions, like in Cartesian coordinates? IJK, right? X, Y, Z. So we're going to use that notation a little bit. Okay. What I want to do is this problem together right here. Okay. I've dropped 3 charges onto like an XY coordinate system. I've given you some distances here. And we're going to try to figure out what the force is on charge number 3. Charge number 3 is our target. Okay? So what are we looking for? We're looking for the net force on 3. And that's symbolically, that's how I'm going to represent it. Okay? And just because there's only a 3 down there, it's telling me that it's the total force. You could write net, comma 3, or whatever symbology you want to do. But I'm going to find that force by figuring out the force on 3 because of 1. Do you see that notation there? Following the book's order? How do I know it's the force on 3? It's the first subscript, right? And what's causing it? Number 1, charge number 1. Are we going to ever have charge number 2 in that calculation anywhere? No. We can figure that out all by itself. And then we are going to add on, and what would the subscript, what's feeling it? 3, and what's making it? 2. And if I had another charge in there, it would be 3, 4, wouldn't it? Right? And so on and so forth. So what happens if I have 10 charges? How many vectors are we going to be adding up? 10. If I have 100,000? 100,000. What do you think? Where do you think this might be going when we have a lot of charges? What happens when you have a big sum of a lot of things you got put together? You integrate. We'll get there. We'll get there. Okay, so now we break it up, right? We're going to do F3-1, we're going to do F3-2 separately. We're actually going to do 3-2 first. It's kind of the easier of the two to do. As a very quick outline of how this would have been done, like using a physics 4a method of finding vector forces and all that kind of stuff, let me just prime you and remind you of kind of what you've done before I show you kind of this new R vector method that I've been referring to. So what I want to do here is I want to duplicate my page. Copy page. There we go. Copied. So do I have 2 copies of it now? No. I copied it. Now insert it. Oh, no. Sorry. It's been a while. I had an insert page. Anybody remember in GoodNotes how to copy a page? Copy. I've got it copied. How do I insert it? It's like they took the button away. I know you can't see what's going on, but nope. Add, paste, it all went away. All right, I'll outline this a different way. Okay, and it won't show up on the paper. If I wanted to find the charge from this one on this one, what do we know about, I didn't tell you anything about the charges. Q1 and Q3 are both positive 5 microcoulombs. Q2 is negative 2 microcoulombs, and the distance A is 0.1 meters. So there are numbers in this problem. Okay, so notice that I made Q1 and Q3 both red to indicate that they were positive, or at least the same sign. And then the blue one is our negative charge. So under sort of the physics 4 AE way, or the way your book does it in the example problems, what do I know about the force between these two charges, this red and blue charge? They're opposites, and what do opposites do? They attract each other, right? So what direction will the force be on charge 3 because of charge 2? Give me a positive x, positive y, whatever. It would be negative x, right? Pulling that way. Pretty easy component to figure out, right? Okay. What is the direction of the force on charge number 3 because of charge number 1? What would its components be? Positive x and positive y. So we would have components like this, and then to add those two vectors together, we do it component by component. So in this method, which is a perfectly fine method to use, I don't want to knock it. It's a good method, but it's one that we are going to, your author is going to get rid of as we go through the next chapters. I want to teach you this kind of better way of using an R vector to figure it out all for you. It's a little bit more algorithmic, but in my mind it's a little bit safer, okay? And it's going to get you ready for magnetism, because magnetism is hard enough without having to learn R vectors. We have to kind of visually figure out, apply our physics rules, which I always think is a good idea. This is a great check step, okay? But then we would have to go write down these vectors in Cartesian coordinates, and away we go, right? Add them all up, we're done. Okay, so that's the old method, the original method, okay? We're going to do the R vector method. And with the R vector method, our Coulomb's law equation is written like this. It's an R vector with an R cubed in the bottom. But remember, there's no R hat here. The reason I teach this is because students over and over again struggle with R hat. Like, what is that? Like, I don't know, I can't see it, I don't know where it points, all that kind of stuff. R vector handles it for you. You don't have to go into the weeds, and your brain doesn't have to get locked up on what all that R hat business is. So if we're going to use this version of Coulomb's law, which is the same thing, it's just like a mathematical sleight of hand, right? Instead of R hat, we're using R vector over R cubed. We can go in and we can find F32. What's it going to be? It's going to be this number, electric force constant, K sub B. Why not? And then what charges are going to be involved? Look at the subscript. 3, 2, right? It's going to be Q3, Q2 on the top. I just write it in. I'm not doing any thinking. I'm more just kind of transcribing my equation into the language of these two charges that I'm working with, right? So what's the distance on the bottom going to be? It's going to be r32. I'm going to leave mine symbolically as long as I can, cubed. And then what's my r vector going to be? Well, it's going to be r32 to indicate like a vector, right? That points from 2 to 3. Okay. R32. Where does it start? What's causing the force? Two is causing it, and 3 is feeling it. I'm going to do this in a different color, but here's my laser pointer, right? Q is causing it, 3 is feeling it. Which way is my R vector pointing? Positive X, isn't it? And now you start to feel uncomfortable because Mr. Balogh, the force was this way, right? Opposites attract. But what are we going to do up here when we put in our charges? One of them's negative, isn't it? It's going to flip it for us. When you do the R vector method, your book puts absolute value signs around the charges. It tells you to, figure out what direction the forces are putting and then put in the magnitude of the charge, ignore the direction. When you're using R vector method, keep the sign in there because the Coulomb's law will be able to handle it. So our R23 vector is going to go like that. So let's see, in blue, I'm just going to draw my vector right on here. It's R32 and it points directly right. Okay, so now what we got to do is we got to figure out the different parts of this. Do we know K sub E? Yeah, it's just a number. Do we know Q3? But what is it? It's 5 times 10 to the minus 6 coulombs, right? What's Q2? Negative 2 times 10 to the minus 6 coulombs, right? So those are just numbers, right? I can kind of ignore them now. But what is the magnitude of R32 vector? Tyler, I think you said it. Your name's Tyler, right? Yeah. Yeah. What did I call you before? Something, okay. Right? So I'm trying to learn names. Instead of that, let's start with R32 vector. And let's not make this any harder than it needs to be. We know the direction already. You told me it was pointing in the positive x direction. What's the magnitude of our vector? It's A, is 0.1, right? So our vector, R32 vector is AI hat. AI, ChatGPT's here. Why is it AI hat? Why is it not negative I hat? It's our vector is pointing in the pot, right? Points from 2 to 3. It's got length of A, right? So now that we know what R vector is, how do we find the magnitude of R vector? It's a dumb question. It's A, right? No? What's the length of our vector? It's A, right? It's the distance 0.1 between the two charges. The vector is right? We're done. So R32 is equal to A, just the magnitude of it, right? One's a vector, it's got direction. The other one's just the magnitude. Hang on for a second. I think you'll see it on the next one. And now I can put this in, right? It's going to be KE, Q3, Q2, whatever those are, over A cubed. Right? I know the distance. I know the magnitude of R. Times AI. Hat. I can clean this up a little bit because what's going to cancel? Now I'm being mathy, right? Oh, and now we're back to the inverse square. Surprise, surprise. It's been there all along. KE, Q3, Q2, all over A squared. I hat, and now I can drop in numbers. 8.99 times 10 to the 9. What did I say? Q3 was 5 times 10 to the... Why am I writing in times 10 to the minus 6? because it's micro, right? And you've got to make sure that you get all of your standard SI units in there. I hat all over 0.1 squared, and I can run that through my calculator, and what I got was -9 I hat. No idea if that's right or not. Don't really care. But I can check something right now. Yes?
Was there a constant given?
K, 8.99 times 10 to the 9? Sure, it's in your book. I don't know if I wrote it down yesterday. I talked about it yesterday, but I don't know. I usually write down 9 times 10 to the 9 because numbers. All right. Check it. Check it. What is it telling me? -9 hat. Does the 9 care if it's negative? 9's a number, right? This negative is with this I hat. It's a direction thing, right? What direction is this force pointing? Towards Q2, right? Is that the direction it should be pointing? Yes. It can handle it. If you give it the sign of the charge and you're using our vector, it will automatically figure out the directions for you. Okay, let's see how this, and that's kind of a silly example. You're like, Mr. Balogh, I could have done that faster just looking at it. You're not wrong. But watch this. Let's do F3.1. Okay, what am I going to write down for Coulomb's law? It starts with K, K sub E. What charges go in? Q3, Q1. What's my distance symbol for distance? R31 cubed, R31 vector. You just start there. It's a template for you to start figuring out the pieces. K we know, Q's we know. It's R31 that we need to figure out. Where does R31 start? It starts on 1 and it ends on 3. Do you see it? Our vector starts on the thing causing the force and ends on the thing experiencing the force. So you come up here and you just draw your R vector straight up like that. Okay. Now we need the components. We need the math of R31 vector. This vector points which way? Positive I and positive y. So we know it's going to have i's and j's in it, right? How far does it point in the x direction? AI hat plus AJ hat. Try not to make your R vectors any harder than they need to be. If you've got a diagram down, you'll be able to just look, right? If this thing were, I don't know, A high and B long, it would be BI hat plus AI hat, right? You can just kind of read it right off your diagram. It's just sitting right there. There's no extra magic or steps you have to go through to figure out what an R vector. If you can draw it from where it starts to what it's feeling, if it went the other way, right, and it was a negative A, positive A, it would just be negative AI hat, positive AJ hat. You can do it in 3 dimensions, right? You can do it in any coordinate system. We're going into Cartesian, but you could do this in the cylindrical or spherical or anything else. All right. Now I've written down what the vector is, its component form. Sometimes you'll have one like, what if it's pointing at 66 degrees above the x-axis? What do you have to do now? You got to do the trig to figure out what the number is, but then you'll have the x and y components, right? So now that we have it in x and y components, how do I find the magnitude? Square root x squared plus y squared, right? Our standard Pythagorean theorem junk. So it's going to be R31 magnitude is going to be square root of a squared plus a squared. Well, that's just a times the square root of 2, isn't it? It's 2a squared. And what's the square root of a squared? A. and the root 2 is left over. It's 45 degree right triangle, so no surprises there. Okay, so what does that mean we can write down for F31? It's K times Q3, Q1, all over, and what goes down here in the denominator? What is the magnitude of R31? A square root of 2, and then that whole thing is cubed. And what goes up here in the top? R31 vector, which is AI hat plus AJ hat. So this bottom term, I'm not going to write it all out. It's got a lot of numbers in it, right? But we know what all of these numbers are now. There's going to be two terms here, right? There's going to be an x direction and a y direction. So we've got to, just keep a handle on that. For charge 3, what are we going to put in? What number are we going to put in? 5. Tell me what I would write. 5 times 10 to the minus 6. And you can put units in if you want. Q1 plus 5 times 10 to the minus 6. Whatever number we get, 0.1 times square root of 2, right? And then my 0.1's, I and j. So when I do all that, when I throw all those numbers in, what I got was 7.95 I hat plus j hat. I cheated a little bit. I factored the a out from the i's and j's because they were the same. If they're not the same, you'll just have, 2 different i's and j's. But I was being tricky. Okay. Now, which way? Which way is that pointing? This tells me that this force is pointing positive x, positive y. And is that where we wanted the force to be in the first place? Yes. Do you see how it worked? Right? R vector can work as long as you give it the signs of the charge. Give it the signs of charge, it will handle the directions of all these forces for us. Okay, now, oh my gosh, now that I've run out of room on the screen, how do we find the net? How do we come up here and get the total force? We add those numbers together. It's 7.95 I hat plus 7.95 j hat plus a minus 9 I hat to get the net force negative 1.05 I plus 7.95 j. And if I wanted to know the magnitude of that vector, since I've got it in components, how do I find the magnitude? Square them both, square root. How do I find the angle it points at? Inverse tangent y over x. That's, from 4a. And I don't want to waste time here. The focus here should be on, okay, there's this method of using R vector. Now, like I've told you, I don't care what method you use. Use the books method where you draw out the force vectors. Use the rules of opposites attract, likes repel. Figure out your components. Go ahead and add your vectors together. They're the same method. It's just they have a different sort of symbolic approach to how they're doing. And the R vector method is going to come, and it's going to be the only way that we're going to be able to handle some of the things in magnetism. So that's why I'm showing it to you now. You can disregard it. I've showed it to you once. Your brain's got part of it in there somewhere, right? You go on, follow the book, follow YouTube, whatever your favorite creator is, whatever, right? I can read physics. If it's correct physics, I'll take it. If I don't understand what you've done, I'll come and ask you, like, what the heck's going on? You can try to explain to me. If it's correct, we'll figure it out together, right? But this R vector method, I'm big on the psychology of learning. It does lessen the cognitive load of the things that you have to keep track of while you're solving these problems. Meaning that really the only thing that you are needing to figure out is what R vector is. Figure that out and you've kind of unlocked the whole problem. The rest of it is an algorithm that you can just move through. So that's why I teach it. Different physics teachers argue about whether we should be doing this at this level. I think it's important. Okay, let's continue on, and we're gonna get into some integrals here today. Okay, And we're going to do that. Your homework is going to be a lot of figuring out vector components and adding those vectors together. So you're going to be frustrated because of parentheses in your calculator and all that kind of stuff. So give it time. Homework's not due this Saturday. It's due next Saturday. But tomorrow's a great day to get started, isn't it? Okay, tomorrow's just fantastic. Now, I used to give this as a quiz, but it was cruel and unusual punishment as a quiz. So let's not quite, you're going to do it together, but I'm going to kind of get you started. All right, so where is the electron? 5, 1, 2, 3, 4, 5. The electron is right there. Okay? And where is our positive charge? 6, 4. So 6, 4 is going to put me right there. So here's my plus Q. There is a negative 4Q charge somewhere that needs to be placed in this Cartesian coordinate system so that the net force on that electron is 0. I want you to find, go ahead and find both, but just the x coordinate's fine. I want you to turn to each other and just talk it out. Maybe draw a picture with each other. Draw a picture, show each other. But I want you to try and figure out where the plus 4 charge needs to be in order for the force on the electron to be 0. There's a method that will only take 1 minute, and there's a method that will take 10 minutes. Let's see which one you pick. Go.
If it's net forces, it means there's nothing acting. So if it's at this angle, it's like this, something has to be charge, right? You have to have the opposite. But if it's 4 times the charge, it's also going to add it. So it has to be a certain distance away.
All right. If you're getting stuck, where are you getting stuck? Like, where are you not getting traction? What are you confused about?
What's negative Q?
What do you mean, like, what's negative Q?
Like, there's positive Q, right?
Yeah.
Negative Q, wouldn't that just be like the negative version?
Yeah, but it's 4 times as much.
So the negative version is 4 times as much?
Yeah, the negative charge is 4 times bigger than the positive charge. So somewhere on this grid, we're going to put a negative 4Q charge and try to get 0 net force. So there's, yeah, no, well, just on the electron. Yeah, just on the electron. Ah. Okay. This is slightly a trick question because it's not two-dimensional. Do you see it? This is a one-dimensional problem. Let me show you. What happens if I say put my negative charge right here? Let's start over. Positive Q in this electron. What direction is the force going to be on that electron because of the positive Q? It's going to be towards it, right? Okay, so it's going to be down this way. To zero that out, what's the only other direction we can go? Going up like that, right? Because if I drop a charge over here and it's negative, then this is going to be pushed that way, isn't it? And if I put it over here, it's going to be pushed that way. Like, nowhere else can I put this except on a line. Get the right line. That acts between those two charges. Somewhere on that gray dashed line is where my negative 4Q has to lie. Because any other position is going to give me some weird components that aren't going to cancel out. And we know that it has to be this way, doesn't it? Because the positive one is tugging it down. So we need the negative one to be pushing it away. So now we've eliminated where it can be. Where can the negative Q not be? Anywhere up here. Why? Because if I put a negative Q charge here, which way is it going to push the electron? Down this way, right? Did you do that?
How about the negative?
Ben Franklin's fault. Okay. So we know that the negative 4Q charge needs to be down here somewhere and not off axis. It has to be somewhere on this line, down on this side in order for me to get zero net force. The only question now is where? Yes?
Wait. If the charge is 4 times larger and an inverse law, would it be
Inverse square.
2 to the power of 4?
Yes.
Farther, so it'd be like 6.
No, you kind of did that backwards.
But it would still be 4 times.
So the first force between Q and the electron is K electron big Q over whatever this distance is. It's the square root of 2, okay? And then the magnitude of the 4Q1, I'm using sloppy notation here, is going to be K E 4Q. I need those two to be the same. So how do I cancel the 4 on top with what I've got left on the bottom? Okay, divide by 4A, but it's an inverse square law, right? So now will I get the 4's to cancel? And that tells me I've got to be 2A away. So where is the negative 4 charge? Yep, 7, 3. It's an inverse square law. It's got 4 times the charge, which means it needs to be twice the distance away to have the same force as a singular charge. Remember, double the distance, it goes up by 4. Do you see now why I don't give this one as a quiz? It really is a kind of a brain melter when it's your first approach at it. But when we're going for zero net force and you only have 2 charges and you're putting a third, it has to be on axis. Anything off axis is not going to give you 0 vectors, right? We need to have that opposition there to get to 0. So try not to make 2-dimensional problems any harder than the 1-dimensional problems that they are. Okay, so that was a good concept. You saw some math, some vectors, and we got some concepts. But now I want to go off book a little bit. This isn't in the chapter yet. So your author pushes this idea into the next chapter. But I want to keep it as part of this chapter because we're talking about charge, we're talking about force. Next chapter we're moving into something called the electric field, which is going to be So we've dumped Coulomb's law on you, the law that covers just about everything that we experience on a daily basis in this universe. And it's pretty complicated to sort out. There's lots of charges flying around. And what we want to do in the next chapter with the electric field, thanks to Michael Faraday, is we're going to try and simplify that a bit. Electric field is going to help us kind of get rid of one of the charges and give us an abstracted idea of what the forces are doing. And it's going to be a better calculation. It's not going to be much better, but it's a step in the right direction. And then in the next unit, we're going to introduce something called voltage, which gets rid of the vectors altogether, which makes it much faster and easier to figure out what's going on. So we're moving in the direction of simplification. We start off really hard because it's fundamental, and then we move towards, okay, how can we actually use it? But before we get there, I need to come back to what I was showing you in lab about that sphere, that funky, truncated sphere problem that we were setting up with the integration. So this discussion, what I'm about to show you, is how we are going to find total charge on objects, which we're going to have to do a lot. Because, quite frankly, the universe is not built up of independent little point charges that all just decide to sit on a Cartesian coordinate system. We're going to have charges spread over the surface of an iPad screen, and then something else coming in with more charge to give it an inductance circuit to know where the finger or the pointer is on the screen, right? We need charges flying around inside your microwave oven to heat up your food. We need charges going down the wires. We need to be able to track complicated arrangements of charges and do it really fast mathematically with. Can you imagine having to do all the vectors on the screen of this iPad just to figure out where my finger is? No, there's got to be a better way, right, than just brute force sort of adding up vector by vector. And that's what we're trying to roll out pretty much this entire semester for you, right, is how do we go from these fundamental ideas to something that is practically able to be done? Because you need a supercomputer to track all the charges in this room and see what they're going to do. But we can do it better with some mathematical, it's not trickery, it's elegance is really what it is. So I want to do several examples of finding the net charge on various extended objects. These will be objects that will be big, be long, like my meter stick. What if we dropped a whole bunch of charge on my meter stick? How would I find the total amount of charge? What if that charge was changing? What if it was more charge on this end and less charge on this end? We want to be able to quickly figure out what total charge is so we can find total force and do all that kind of stuff. So these are representative geometries. We're going to do it in a line. We're going to do several surface areas, and then we're going to do some volumes. And we're going to do it with all the common shapes that we use in physics to put the universe together. Those shapes are lines, cylinders, and spheres. Anything else, we're going to approximate with one of those, sometimes cubes. Okay? And so there's a joke that goes in physics like, how do you figure out the volume of a cow? Assume it's a sphere, 4/3 pi r cubed. Right? Find the average radius of the cow. We're done. Right? Again, we're not caring about how accurate it is, but we've got T-shirts with spherical cows. You can find them on Amazon. All right. So what am I talking about? Let's just get into the nitty-gritties, Mr. Balogh. Okay. So let's say that I've got a metal bar. Okay. And I'm going to drop this metal bar down on the screen. Okay. And I'm going to charge it up such that it has a linear charge density of the amount of charge I put on it divided by its total length. So this thing's got a total length, right, like that. And I've gone ahead and put some, call it positive charge on there, right? Just dumped it on there. Notice that I've used that density that I told you about in lab, not as a mass, but as a charge density now. Density, again, is a ratio, right? It's a ratio of something to a physical parameter, in this case, length. So we're going to have 3 of these. And you know what they are already. What are the 3 that we're going to have in terms of charge? No, Q over length for lambda, sigma Q over surface area, and rho Q over volume. And so how do you know if you're dealing with mass volume or charge per volume? How do you know what rho is? You have to look at context, right? Are we talking about charge? Are we solving for charge? Then it's charge density. Are you looking for mass? Then it's mass density. It's the same symbols that are used for the mass ones, but here we can use them for charge. And we do this all the time. We'll use charge density, mass density, neutron density. Like, you can do all kinds of things, right? Put it in the numerator, come up with a density. Okay, so I know that that's my charge per unit length, whatever those things are. I'm not giving you any numbers, okay? And our goal is to find the total charge on this rod. Now, because it's a conductor, it's made out of metal, the charge spreads itself out uniformly and is the same small amount everywhere along this rod. But as I taught you in lab, start with what you want to find. I want to know the total charge. And how are we going to find the total charge? We're going to add up what? A bunch of little segments of charge. That's not the hard part. The hard part is, what the heck is dq? But you now know, maybe remember, maybe not, how do we get dq into a distance that we can actually integrate over? What's the secret? It's sitting right here in this density thing, right? Because it can be Q over L, but it's also, if I take a little piece of charge, I also have to take a little piece of length. And this isn't a derivative, it's a ratio. So if I want to solve for dq, what do? Multiply. This will be lambda dl equals dq. I just multiply both sides by dl. This is just algebra. And then I can make a symbol switch. I'm sitting here on an x-axis. What direction do I want to integrate? In the x direction, right? I'm finding a little tiny piece, and I'm going to add up in the x direction. So my little piece of length is a little piece of dx. Woo. Oh, darn it, I had it right there. Anyway. Always look at your notes, Mr. Balogh. Lambda dx equals dq. Okay, so where does this dq go? Goes right there, doesn't it? I now know what it is. Lambda dx. And before I can go any further, I need limits. I need to tell the integral where this rod is. It doesn't know yet. It knows it lies along the x-axis, but it doesn't know where to start and it doesn't know where to end. So where's it going to start? At 0. Where's it going to end? At L, however long it is, right? I didn't give you a number. Okay. Since the charge density is uniform and the same everywhere on the rod, it is a constant. What can you do with constants in an integral? You can take it out. And what's the integral of dx? It's x, evaluated from 0 to L. So what's this going to be? Lambda times L. We've come full circle. Because Q is equal to lambda times L. Well, of course Q is equal to lambda times L. That's what you wrote down right there. This is stupid, Mr. Balogh. We got back to where we started. We had to do an integral to do it. I want my money back. It was easy and it was stupid because it was uniform. How often are things perfect? Right? So, what happens if instead our charge density wasn't nice? I want this in red. What if lambda was equal to ax cubed? Let's say functionally we know how our charge is changing. Maybe we've gone out and measured the charge deposited on an airplane wing, and we see that it follows this pattern. Okay? Can we find the total charge on the airplane wing? Why would we want to know that? Do we want people to die when the airplane comes into park at its gate? No, we want to be able to get that charge off, right? So it's better know how much charge so we know what size cable so we know how to tell the technician to be safe when they're plugging it in. Okay, so I want to find what? Yes. The first thing that happens when a plane comes into park is whoever drew the short stick that morning gets to run out with a cable in hand, and they plug the plane in. It does two things. It discharges the electrostatic buildup because the plane's been moving through the air, and it gets all this static electricity on the outside. It plugs in and grounds the aircraft safely. It's a big plug that goes in. And it connects the airplane to the airport's power so that the airplane can turn off its engines and power the air conditioning and the toilets and everything else. Very important when you have humans on board. Okay, we're looking for total charge. How are we going to find it? This is the easy part. Nope. We're going to integrate all of our little DQs. Don't skip this. This is your pattern. You don't write this down, your brain's not going to have an anchor on where to go and what to do. Okay, now that that step is down, what's it telling you to go find next? What's DQ? What's DQ? We already did it. It's lambda dx, right? We're just recycling here now, okay? So this is lambda dx. What are the limits going to be? 0 to L, but this time lambda can't come out. We have to write in what lambda is. It's ax cubed dx. What can come out now? Now we're just doing math. What's the integral of x cubed dx? The fourth over 4, evaluated from 0 to L, which is a L to the fourth over 4. And there would be the total charge on that rod with that lambda on it. And now we can do any lambda, right? If we know the function that lambda is running, we've got it. Focus on the process, not the answer. The answer here is, I don't care what it is. It's that process of laying out, what do I want? I'm going to integrate to find it. And the key that's going to make it so that I can set up an integral are these density relationships. Notice, all of these densities connect. I've said it over and over again. They connect what we're looking for with physical space. Right? That's the connection that we need to be able to integrate. It's hard to integrate just over charge. What does that mean? But integrating over an x, y, or z, or a theta, or a phi, or whatever, oh, we can do that. We've learned how to do that. We're learning how to do that. Okay. Now we go into more dimensions. Okay. I showed you a little bit in lab that there are many different ways to cut a cake. And same is true for cutting up a sphere. And so I want to talk about onions. I want to talk about how ogres are like onions. Yeah, is that movie too old now? No? Okay. Well, you guys stopped understanding my Back to the Future and Ghostbusters references. So, not you guys in particular, but like classes I've noticed in the last few years. I'll drop a Ghostbusters reference and it's like, nobody understands. All right, so let's say we have a sphere of charge, okay? Something that's roughly spherical, and we've gone and we've measured that the spherical charge density is AR squared. I like to use A as like a number, right, without having to write the number now, okay? And we want to find the total charge on our sphere. I don't like drawing spheres because they always end up looking something, I don't know, like that. Does that look like a sphere? I don't know. It looks like somebody that's not unimpressed.
I was going to say it looks like a disinterested.
Yeah, disinterested face is what that looks like. Anyway, okay? But we're going to roll with it. Even if we can't sort of see it, we're going to try to hold fast to the process. What are we looking for? Charge. We are looking for charge. How are we going to find it? We're going to add up all the little pieces of charge. Again, that's just a template, right? There's no magic there. You're not thinking about that. It's just big equals integral of small thing. Okay. Now the hard part. What's dq? How are we going to link dq to physical xyz's? Can we use lambda? No. Can we use sigma? No. We were given a rho, weren't we? How many dimensions is that? It's 3. But remember, we don't do 3D integrals in physics. Well, we do, but we don't. We know that rho is charge divided by volume. Total charge divided by total volume. And we can take a small part of that charge divided by a small part of that volume and get the same number. So solving for dq, I will have rho dv. That, again, I skipped over the algebra I did there, but I just multiply both sides by dv, and then I just kind of switch the order of my equal sign. So I know that this thing is going to be rho dv. While we're here, if you're using sigmas, which I'll do an example of, what's dq going to be? Sigma dA. dq will be rho dv. Rho dl. Right? They're the same all the time, right? So that's kind of automatic, all right. But now the real problem rears its ugly head. In a line, it was easy. Oh, the line was that way, it's dx, right? What if the line's vertical? dy, right? What's dv? How are we going to cut up this sphere into pieces that are easy to work with in an integral? The answer is not dx, dy, dz, because that's Cartesian coordinates, and spheres don't like Cartesian coordinates. It's not, yeah, okay, so we've got to run this sort of trick. Remember, this integrand has to have units of charge. We're finding charge, and the integrand has the units of charge. We've already got the charge density, so that dv has to have units of volume. So we know it must have units that are meters cubed, right? When we're done, whatever dv is, it better have meters cubed, because it's going to be multiplied by a coulomb divided by a meter cubed, and we want coulombs to end up. So what is my dv, right? That's the question. How many different ways are there to cut a sphere? Too many. But as you can see in the picture here, I'm going to go for a layered approach. This is like a cross-section of my onion. You know, onions have layers, right? And we can find the volume of like an individual basketball type thing, right? So what I need to find the volume of a basketball-y shaped kind of thing is what? I need like a surface area and then like a bump out from that surface area. Okay, I've got to lock in a change somehow, and the integral, the density function is screaming at me as to what direction I need to be going. Look at rho. What does rho say? What does rho depend on? It's not A. A is a constant. R, the radius, right? The radius of this sphere. Which way does R go? Out, right? So, oh, by the way, R is radius here. You're welcome, I guess. I don't know, right? It's in the picture, right? But since the density changes in R, does it change in any other direction? Does it change depending on where around the sphere we are? Or what latitude we're at or anything like that? No, it only changes going outwards. And so that tells you something about what you want your little d to be. What do you want your little d to be? dr. Just like our line of charge, the dl was dx because that's the way it was changing. This changes as r squared, r cubed, what am I doing? R squared, right? So I want it to be a dr. So if I'm bumping outwards along the radial direction, how do I get the rest of the volume? What do I need? Surface area of a sphere. Oh no, what's the surface area of a sphere? There's a 4 in it. Pi r squared, yeah, okay. The surface, so my dV is going to be the surface area of my sphere times dr, which is going to be 4 pi r squared dr. I've taken the surface area. This is hard because this is just a slice, right? It's really hard in 3 dimensions to show this on a 2-dimensional screen. So this is like a slice through the sphere. We found the surface area of the inside of the basketball, the inner lining of the basketball, and we've gone punk, the thickness of the basketball out in dr, and that's now a volume, right? It's the layer of an onion, a singular layer of the onion. And if I now want to find the total volume of the onion, what am I going to do with all my individual onion layers? Add them all up. And so I take this dV and I throw it into my equation so that my Q is equal to rho 4 pi r squared dr. And now that I've got it in a kind of a mathematical physical space, I can put my limits of integration on this. Where does it start? At the center of the sphere. Where does it end? Wherever the radius of the sphere is. Okay? Am I done? Am I ready to go yet? I've got to substitute one more thing. Rho. Rho is not a constant. It's a r squared 4 pi r squared dr from 0 to r. The integral, is now set up. This is the hard part of physics 4b. This is where all your brain power is going to go in. Because once we get to this step, what do you do now? Right? Just turn on the math muscles and go. You've done, this is easy. The 4, the pi, the a, all goes out. What's the integral of r fourth? dr. R to the 5th divided by 5. Right? That's the easy part. You're going to get there and go, oh, look, I can do integration by parts. Thank goodness. You never thought you would be grateful to be able to just say that, right? Because it's going to be such a hard fight to get it set up in the first place. And you're newbies at this. Has anybody ever seen this before in your math classes? They never cared. You did? I want to talk to your math teacher. It's a good math teacher. Okay? They don't start there with math. They are all about how do you do that, right? Down there at the bottom. When everything in physics and engineering and science, we're all about the top, right? We're all about getting there and communicating how we're getting there and setting it up correctly. And we're gonna practice this a lot, over and over again. You're gonna do it. And you're gonna fight. Your desire to do things as fast as possible, as easy as possible, and not have to pay any price to do it, is to try to skip all of this. Let ChatGPT set it up for you so you can just do the integral, right? Don't let it do that. I'm going to be looking for, can you show me how to set it up? Integration, yeah, you got to be able to integrate. But it's not as important as being able to put all the pieces together. All right, I already did the integral, but I'll do it again. A 4 pi r to the 5th over 5, 0 to r. So this is 4 pi a r. There we go. Okay, in coulombs, because it's a charge. It's just a number that's with rho. Yeah, whatever number goes in front of rho. Okay? Okay. Let's do cylinder. What?
So, like, when when you're working these things out, basically any surface area given times a dr, a change in
Can be, it doesn't always.
would give you, not always, but for the most part, gives you a volume.
Well, yeah, that's three-dimensional.
Because it's an area with another dimension, right?
Yep. All right. We try to not to ever. All right. We are looking for the charge on the cylinder pictured on the screen. The cylinder has a surface charge density that has a function that looks like a plus bz, whatever those numbers are, but the z is the variable, so it tells you how this surface charge density is changing. Which way is it changing? In z. So obviously, when we're done here, we're going to be integrating which way? It's z, right? We've got to add up in the z direction. So you have a little bit of guidance. You can tell some things from your charge densities. Okay, we also know that charge density is equal to dq over dA. So that means my dq is going to be sigma dA. And now the question becomes, okay, what's dA? How do I cut a cylinder into pieces parts that goes with how my surface charge density is changing? This is going to be cake layers, isn't it? Going up the z-axis like this. That's pictured on the screen right here. Okay, so you can see an individual cake layer that's come out. What do I need? Do I need the length, surface, or volume of that cake layer, that little chunk? I need the surface area, not the volume, right? It's not the volume of that cake layer, it's just the surface area of the strip around the outside. So how am I going to figure out what my dA is? It's got to have two parts in it. One part's going to be like a dz, but how do I get the surface area? I can do a circumference of a circle times dz, and that gives me the area of that strip, doesn't it? So what's the circumference of a circle? 2 pi r dz. And now, is 2 pi r dz an area?
Yes.
It's got two dimensions in it, right? It's got an r and a z, meters squared. We're on the right track, probably. Sigma is a plus bz. And I've got 2 pi r dz. Actually, it's not r in this. I could see it's a, isn't it? It's a on the diagram right there. It goes out to a. Where does z start? Got to put limits on here. 0 looks like it's starting at the origin. And where does it go? Up to L. Now we integrate. I'm not sure what I got. I did a bunch of stuff. It's not that bad. Because the 2, the pi, and the a all come out, don't they? Are those things changing in the integral? Nope. So, yeah. I'm just going to cut straight to the chase. This is 2 pi r a l, 2 pi r a l plus bl squared over 2. There we go. Coulombs. And how do I know these things keep coming out in coulombs? Because I'm putting standard units in. My standard areas, my standard lengths, right? Meters, all that kind of stuff. It's going to work itself out. Okay. But what if instead the surface area changes as cosine theta, a cosine theta, meaning that the charge isn't like changing as we go up and down the cylinder. The charge is changing as we go around the cylinder. What kind of cylinder would have charge that's changing around the outside surface? A wheel. Rubber on asphalt. Rubbing causes charge to happen. No, call it rubber because it's made from rubber, right? But knowing charges on wheels could be important. Inside of a machine, for a car, whatever, I don't know. Could be. It's probably been figured out a lot. But let's say we knew that and obviously in reality, are the charge densities this simple? Nice and easy, integratable things? No. You need to go get a computer and do numerical methods to solve some of these horrible, horrible setups. But getting the setup down is crucial. We're, of course, using simple mathematics because we want to focus on setup and leave the math to be easy. Okay, what are we looking for? How are we going to find it? That hasn't changed, right? So we know that this is going to be sigma dA. But how does our dA have to change? What's the variable here? It's not radius. It's angle. It's theta. It goes as cosine theta. A is a constant. There's no r's in there. It's okay. Don't feel bad. Don't be afraid to be wrong. Right? It's going to take a little bit. So how do we find the surface area of one of these like vertical strips, right? We're going to get a little tiny strip and then we're going to add them up all the way around. What's the area of that strip? It's a rectangle. And so what does that mean it's going to be? The height, the length in this case, right? Times. It's not just r. We're going around. Close. Arc length. So like looking down at the top, right? We're doing these kind of cake wedgie sorts of things. The distance here is the arc length, isn't it? And so it's going to be L, the total height, times the arc length, r d theta, right? Not just r theta. Theta would be all the way around. D theta is a little tiny piece. So to get that surface area, I needed the height and the little chunk of arc length as we're going around. And you're sitting there going, Mr. Baylor, there's no way I would have been able to guess that. Of course, knowing is how you know stuff. Why do I look smart? Don't answer that question. Why do I come across as intelligent or smart? Or, oh, you're a physicist, you must know everything. It's not because I'm smart. Movies? No. It's because somebody's told me about it. Right? Where did I learn my stuff? Sitting in a seat just like yours. Same look on your face. There's no way. Do you know how many times I said in college, there's absolutely no way I'm going to be able to ever do this ever? It's all the time. All the time. I'm not an English major. I'm a physics. I hold a master's degree. You can call me master. But what did I do? I just kept going. I didn't care if it took me 2 years, 4 years, or 10 years. Let's face it, I never left school. It's been 2025. It's been 27 years that I've been in school, and I still don't get it. Right? I never left. They didn't let me out. No, I chose to come back and teach, right? So, yeah, I know, like, you sit there and you go, oh my gosh, there's no way. There's just no way. Well, now you know, right? You're learning the methods and the tricks and the things to think about, and your brain's going to start, and you're going to start being able to invent things on your own, and some of them are going to be right, and most of them are going to be wrong, and you're going to find out. Okay? So just keep going. And when you don't know where to go, what do? You keep trying, you ask. This is where other people come in line. This is where grasp happens, right? All that kind of stuff. Okay, so let's see. Get off your soapbox, Mr. Bale. Just teach us something. Sigma is what? A cosine theta. My dA is now L times, and it's R, but it's A, isn't it? Because my radius isn't changing. This R really is A. The radius of my cylinder isn't changing. It's not in the density. And I could leave it as R as the radius, but it's A. Same A as we've been given. LA d theta. Did I get everything in there? See, I have to check my notes. Can't do this all. L, R, A, and then... Yep, okay. I'm assuming those two A's are the same. I don't know. What am I integrating? Where am I going? Where am I starting? Theta goes from 0 to 2 pi. Right? Look at the thing that's changing. It's d theta. So we got to do language of d theta. All right. What comes out of here? Let's see. It's an a squared. It's an L. That's it. Cosine theta d theta. Oh, dear. Integral cosine theta is sine theta?
Yeah.
Or is it negative sine theta?
Because you do the derivative of sine of it.
2025, I took calculus. It's been 41 years since I first was introduced to this integral. I'm old. No, 31 years. I'm a decade off. 31 years ago, that I was first introduced to this. What's 31 plus 19? Oh yeah, that's okay. I did that right. So it's been that long since I've been introduced to that integral, and I still can't remember which one is which. Is it just sine theta? Because the integral of sine theta is negative cosine theta, isn't it? You could be totally lying to me, and I wouldn't know. It doesn't help. Okay.
Your bounds can't be 0 to 2 pi.
Why not?
It's a sine function, isn't it?
Oh, not an integral. So AL sine theta evaluated. Uh-oh, Girk's already seen the problem. What's the sine of 2 pi? 0. What's the sine of 0? 0. We just came up with a really complicated way of writing 0. Why is it 0? Because it goes as cosine theta all the way around once. You start at 1, around, you go negative 1, and you come back to positive 1. What's the total amount of charge on that going to be? 0! Could have saved a lot of time by thinking. You learned how to set up an integral and find a really complicated way to write 0. We will continue on with this on Tuesday, and I'm going to start chapter 20, whatever it is we're on, 2. Okay, because I'll finish up chapter 21 and go to chapter 22. On Canvas, there is a PDF. What does it mean to integrate? By one of my advisors. It's there for you if you want to get into seeing all the different ways you can cut stuff up. It's all there. It's on Canvas. Go look at the course content for this unit. Have a great weekend. I will not see you on Monday.